Thank you. Thank you. Thanks everyone for taking some time and attending this talk. So today's presentation is about what we have developed in the last 12 months, which is DIP, or Decentralized Identity Provider, and how it can be used to support on-chain credential verification. My name is Antonino. I'm a core developer at KILT, and I am primarily involved in developing identity primitives. So I would like to start with a recap of the DIP architecture as it's currently designed. The system relies on 3 actors. We have a user, which has its identity set up on a chain, which is the provider, and a chain where such identity needs to be accessed, which we call relying party or consumer interchangeably. The provider and the consumer each have a pallet in substrate terms, which allows the identities to be accessed. And although both chains are connected to the same relay chain in this V1, in the current V1 version, they're not required to have XCM channels open because everything happens via state proofs. This said, for a user to use their identities cross-chain, they first have to have an identity in the first place. So the concept of what an identity is not even specified as part of the protocol, and it's defined by each provider. It could be, for instance, a simple account address. It could be a decentralized identifier. It could be an entry in the identity palette, a PNS name, or something else. So regardless of what an identity is, the palette on the provider chain allows users to generate commitments of those identities, which are like snapshots, if you like. This represents the state of a user's identity that is being made available for cross-chain utilization. Any updates to the user's identity will most likely result in updates of these commitments if the changes are relevant to be reflected on other chains. And the commitment itself is stored in a storage map on the provider chain and forms the basis on top of which the cross-chain state proofs are generated. Once the block where the commitment was generated is finalized, the identity can now be used on all the other connected parachains. And this is done via the DIP consumer palette, which exposes a dispatch as call. And I will provide more details on this later. In short, the call allows a user on the consumer chain to act as a user on the provider chain. So for instance, if a user has a KILT identity and they want to use their DID on Embarch to participate in some governance, they can now do that. Or if a user needs to prove some kind of ownership of a GitHub handle, which has been attested somewhere, the protocol would allow a consumer chain to require this bit of information over the DIP protocol. And this avoids the need to set up a whole new collective to just achieve the same goal. Or if a user is already part of a collective, the DIP protocol can be used to actually share cross-chain membership proofs that a user is already part of a collective on some chain, which gives them access to do some operations on another chain. Because the protocol is not message-based, as it's the traditional XM design, but it's rather pool-based, the same commitment, once it's finalized on the provider chain, can be used on all the other consumer chains without having to push the information to each of them. And this is because, again, the information is pooled and provided by the user when they want to accomplish something on a consumer chain. So I will briefly dig deeper into how the identity commitment generation work and how the proof verification works. They're basically trait-based, which is what Rust is good at. And this is to show the generic approach that we've taken when we design the cross-chain interactions. Because one of our goals is, of course, to collaborate with other projects, both on the provider side, so projects that have identities, and also consumer side, so projects that want to consume those identities. So the generation of an identity commitment is a 2-step process. This is a little bit more technical. The identity of a subject needs to be retrieved from the chain state. And this is the identity provider trait, which takes an identifier and returns some associated value for this identifier. And the provider, again, makes no assumptions what the identifier is and know what the success type is. And this is up to the provider to specify these types. And while the identity details, after the identity details have been retrieved, then this identity commitment generator trait, which takes this as input and provides some sort of output for a specific identity commitment version. And this is, again, specified by the provider runtime, and the protocol makes no assumption about it. Yeah, so as I said, the identifier is generic. The details, which are retrieved from the chain, is also generic. And all of this happens via the commit identity call, which is exposed by the provider palette. and effectively marks an identity as ready to be used cross-chain once on the provider side. In the case of KILT, specifically, the identifier is a KILT identifier, as many of you know by now, I hope. The details of a KILT identity is the aggregation of on-chain information, which consists of multiple different DID verification keys, a Web3 name, which is a user-friendly name that a DID can claim on the KILT blockchain, and other accounts that users can link on the KILT blockchain. And in its V1 implementation, the commitment in our case is a Blake2 root of a Merkle tree, which is formed by aggregating all of these leaves together. But now moving on the relying party, which is the consumer of cross-chain identities. We have so far a similar structure, which is one pallet exposing a single call. It's the dispatch S, which works on a conceptual level very similar to the utility dispatch S calls that most Substrate developers are probably familiar with. It allows the submitter to act as a different origin. In the case of the consumer pallet, this is a deep origin, which again is specified by the consumer. And in the case of the utility pallet, is any origin available to the runtime. And if the proof is verified successfully, as the trait implementation returns, then the deep origin is created and it's passed to the nested call that is specified as part of this extrinsic in the last parameter there. This is the identity proof verifier trait, which defines the verification logic, what a proof looks like, and what information is made available to the nested call if the proof verifies. And there's a bunch of other inputs to the function, which are, so the call, which is the dispatchable on the consumer chain. So we're talking about the consumer chain here, not the provider anymore. We have the subject, which it's the definition of what an identity is, and this should match what the provider chain defines as a subject. We have the submitter, which is an account address on the consumer chain that is trying to submit a transaction and pay for the fees. We have the identity details, which are additional details that can be stored about the subject on the consumer side, and I will explain why they're there. And then we have the generic proof, which is defined by the proof verifier logic. Specifically for the local details, you can imagine that a cross-chain operation, some operations require some sort of cross-chain signatures, and signature requires some mechanism to avoid replay attacks. So in this case, for instance, a nonce would be a logical element to store on the consumer side. Whenever a user is trying to do something, they provide a signature and they register the latest used nonce locally on the consumer chain, because it doesn't necessarily belong to the commitment, so it's not part of the identity as such, but it's part of cross-chain identity utilization. So to recap, there's information that is inherent to a user's identity itself, which is most likely tracked in the commitment on the provider chain, and then there's information that is specific to only cross-chain operations, which is tracked on each consumer. Then here is the same representation of the same identity commitment, but used by two different chains. So while the reference commitment is the same, each consumer chain could technically implement a different verification logic, expect a different proof type, do something else inside the proof verification, and also track different locally valid details for the same subject. So one might have cross-chain signatures and might want to track nonces. The other one might want to track something else, and I provide examples later when I talk about potential way to implement on-chain credential verification. So given this not very short explanation of the building block of the DIP protocol, we can see how like an on-chain flow for verified credential, for verified KILT credentials could work. So from this bit on, the talk is more KILT specific, and how we envision ways to do on-chain credential verification. So we have different alternatives. Of course, the goal is to also involve community into designing ways to solve a larger set of use cases. Alternative number one would not change much the way that identity commitments are generated on the KILT chain, so it would still remain a Merkle root on the KILT chain. The interesting bit comes during the cross-chain proof verification. Here, the proof itself could actually be some sort of ZK proof, which reveals parts of a KILT credential that the user holds in its wallet, privately holds in its wallet, or a derived representation of it. There's also mechanism that we can take and input a credential and produce something else, on top of which ZK proofs can be generated. And this credential, for instance, could be a KYC or Know Your Customer credential. So the subject DID itself comes from the cross-chain proof, where the subject can say, this is my DID on the KILT chain, and I can provide a Merkle proof for it. And attached to this DID, there's a bunch of information which I can reveal in a ZK fashion, revealing some claims about me. At the moment, what such ZK proof looks like, we don't know yet. We have a few ideas, we're exploring a few options. But as I said before, we would like to start chatting with other projects and experts within the community that can provide insights to solve this problem, and also with other projects that could benefit from this solution. We can sit and try to catch something together, because, as I said, DIP is quite generic, so it allows us to do many different things and change over time without necessarily requiring expensive runtime migration, because most of the logic is in the verifications, in the provided type for verification. But yeah, whatever the proof format, once it's successfully verified, the call is dispatched, as I said before, and think about trading on a DEX, for instance, where you might have some requirements, or governance participation where auditability and accountability is necessary. Option number 2 takes a slightly different approach. It involves an off-chain authentication step. So a user with a KILT ID visits a DApp for a service that they want to use on the consumer chain, of course, and they authenticate with their DID wallet. The DApp performs the necessary authenticator procedure off-chain. We have a API definition how a user can verify and present claims from credentials to match whatever the verifier is expecting. And when this verification process completes, the DApp can store something under the user's details on the consumer chain that marks them as verified, whatever verified means. It does not have to specify what they were verified for, since that's information that is internal to the service, but it would just store on chain some sort of evidence regarding the user's authentication. And then a user would just use a simple cross-chain proof where they reveal their DID, and then the runtime would be able to match whether a specific DID fulfilled a certain set of requirements that the service already pre-recorded on the chain. So this, as I said, takes a somewhat different approach from solution 1, relying more on off-chain interaction, but also a more user-friendly experience when it comes to authenticating, because it would look no different than what people would do today to log in into a website with a wallet. Approach number 3, potential, is somehow building more in the commitment scheme on the KILT chain, where we can envision a way for users to somehow specify what claims they would like to make available for cross-chain proofs, and these claims or their representation being included in the commitment, and then everything would be cross-chain proofed on the consumer chain, where the user also reveals what are the claims that they want to make available to the consumer chain. Again, for the KYC claim, they can prove that they were verified at some point in the past by some entity, and that might be enough for the use case. Okay. There are potentially many other ways of verifying credentials or individual claims in a way that is scalable and privacy preserving. The DIP protocol just defines the minimal users interactions and system components, such as pallets. But now we want to start collaborating with projects to come up with solutions that are built on top of the protocol to fulfill a wide range of use cases. As I mentioned, governance participation, what we've seen is becoming more and more important, and accountability is one use case where this property could be needed. And also finance-related use cases are another interesting one for on-chain verification at the transaction level. And some of you might be wondering why not do as much of this off-chain. Well, because code is law, and having requirements enforced within a blockchain's runtime opens up participation to purely on-chain structures like collective DAOs and even entire blockchains, which often do not have capabilities to perform off-chain operations or do not have any sort of crypto capabilities like holding private keys. Okay. Yeah. So the bottom line. The DIP protocol is a generic framework, not a solution for cross-chain identities. KILT implementing it is a solution to some use cases that benefit from what KILT offers. But of course, we are aware that KILT is not the solution to all the problems, and there are other solutions which can fit those use cases better. But these use cases should be implemented definitely on top of the DIP protocol by other providers and consumers. But what also we are looking at as part of the V2 is to exploit the capabilities of trustless bridges, which are soon coming to Polkadot, to provide smart contracts on EVM-based chains, the same set of features that fellow Polkadot parachains now can access natively inside the Polkadot space. This means that in the future, KILT users will be able to use their DIDs on Ethereum whenever the use case requires them to. The protocol components have been developed thanks to a Polkadot Treasury grant last year. We have developed the KILT provider pallets we have deployed the KILT provider pallets on our testnet, which will soon be migrated to Paseo whenever that's made available, and it's coming to SpearNet in the upcoming runtime upgrade. We will also move the code to a new repo shortly once we have finalized the last details, and we would like to onboard more providers and consumers to collect their implementations of the trades that I showed before, and try to foster an ecosystem where new projects coming into the space, if they need some sort of identity solution, they can either choose from existing identity providers based on what they offer and their needs, and they can also reuse some verification logic other projects have already developed, or if they don't find anything, it would be great if they can contribute with their verification logic for this specific use case, for instance, a ZK-based use case. So yeah, a call to all the providers out there. We're happy to engage in discussion and improve the protocol based on the feedback and the outcome of those discussions. And as for KILT, we're more than happy to start discussing with projects how KILT DIP, so our implementation of the KILT protocol, can bring them benefit, given the tech stack that KILT has already developed for both off-chain and on-chain interactions. Yes, that was my talk. Thank you. I will leave some time for questions.
All right, you can have any question for Antonio? Anyone want to ask anything? Any question?
Yeah, that's my Telegram handle, so you will end up texting me and then.
Yes, or ask him in person on Telegram. All right.
Hello.
Oh,
yes.
Oh yeah. Hello. The awesome presentation.
Thank you.
Cool protocol. Like, can I get this presentation with the code examples for me, or you can give me QR code to download this?
So yeah, there was a QR code here. This is the
GitHub.
link.
GitHub.
Yes, this is a link to our Node implementation.
Okay.
There's a template project where you have a provider template and a
Okay.
consumer template, and they are able to already communicate with each other.
I already get
All right.
this.
Okay.
I
Then
already
yeah,
got this.
that's probably the entry point for you.
I will find everything there.
Absolutely. Yes.
Thank
If
you.
you don't
Thank
find
you.
anything, you can text me at this other QR code.
Yeah, I also already have you in contact. Thank you very, very much. Thank you for your presentation.
you.
You are awesome. Thank you.
Awesome, awesome.
Oh, that's
We have time for one more question. Anyone want to have a question with Antonio? Anything want to ask? All right, then let's get a round of applause for Antonio. Thank you so much.
Thank you.
Amazing presentation, man.